Hi everybody. Just wanted to give you a brief introduction to Java so that you could have a little insight into what's going on in the course. I just wanted to share with you the work that you'll see in the Java for Programmers book. And you know that Java is a programming language, but it's more than that. It's also a technology that supports the language, and it includes things like a virtual machine, a development kit, various IDEs that go with it. All are a part of the programming language, and it's important to know that we need good languages because good languages are giving us good tools. We shape our tools, and thereafter our tools shape us. One of the problems with dealing with a computer that's different than our brain, the so-called biocomputer, is that it's going to do processing that needs to be directed at a detailed level. And it is that direction which we call code. And we call it code for a reason. I think the reason we call it code is because it's sometimes true that we need to encode our thinking into something a machine can process, and we have to decode what has been written either by us or by others in order to see what it is we're directing the machines to do. And so one of the problems that we have is that we need to structure our data, and having strong data types is fairly important for us in order to make us comfortable with an environment that allows us to create programs that run reliably. And oftentimes people try to trade off reliability for speed, but with Java we always want to focus on reliability versus speed. So my basic idea is that I present to you this notion that Java is a different kind of programming language than other kinds of programming languages. A, because it's object-oriented, and B, because it runs on what it would be termed a bytecode environment. Bytecodes are reduced instruction set computer codes which run on a virtual machine, and the virtual machine enables us to take the bytecodes and move them from one platform to another. We like to do that in part because we want to change what's known as the HTML model of execution. HTML is your hypertext markup language. It's used by a browser for the presentation of content, but it's more than that. It's also a pointer to things that allow us to decode what we call process data. And in the case of process data, we may have things like images and audio and various kinds of multimedia files. And if we invent our own data types, we need some mechanism for doing a decode. And so the browser becomes this monolithic application with various add-ons, which we sometimes call plugins or helper applications. And these helper applications are invoked when certain data is seen in the data stream called a MIME string. That's a multi-purpose internet mail extension string. And it identifies the data as it comes in, even if it's just binary data. And it can say, you need Excel to open this, or you need a GIF decoder, or you need a JPEG decoder, or something like this. And all of your major browsers have access to these sorts of things. So when we look at some mechanism for retrieving that data, we typically go over a network. Now you can do internetworking, lowercase I, or internetworking with a capital I. When you're going on the capital I internet, that's the big internet of things. And so now you've got browsers going out to the network, getting all of this process data, and trying to communicate to your computer with that process data. And the only way to make that work is for that computer to have a decode capability. And so typically when we think about our internetworking, is we think about a collection of nodes. And the nodes do store and forward. These are network interface cards or mechanisms like routers, which essentially do the data packet networking for us. And so once we are able to get data reliably connected to the computer, we then need to process the data. So when we think about the web, it really is a relatively recent invention. It dates back to about 1994, and it imposed a graphic user interface on the internet, and that GUI came about because you were able to create browsers that use HTML for the presentation of the content. But the browsers still need some mechanism for decoding binary data for presentation, and that binary data can include all these different other things, and oftentimes they are built into the browser, but sometimes they're not. So if you have a PDF file and the browser can't decode it, maybe it uses a plugin from Adobe to decode the PDF file and present it. Other things that people use for plugins actually enable executable content, and this includes things like Shockwave, or in our case Java. And so with executable content, you can have programs that you run on demand. So then that begs the question, if you could run a program on demand just by visiting a web page, would you? And that's what happens with JavaScript. So we need to do something to make those programs safe. Because if you run a program on demand and the program says, oh, I'm going to upload all of your data, or I'm going to wipe out your disk drive, or I'm going to send death threats to the president, you don't have much control over those things unless you have some mechanism which gives you security. So you have to run your executable content in what's called a sandbox. And that sandbox gives you security through feature limitations. And so that is part of what's known as the Java model. So we can keep adding formats that we can decode using the Java model, because the Java model enables us to run programs on demand, running them automatically without your permission when you visit a web page. So therein lies one of the basic elements of running a program on demand. A, you have to have some mechanism to stop the program from doing untrusted things. And B, if the program is trusted, you need to have some mechanism to go and trust the program. And the mechanism we use for trusting a program is we use a code signing mechanism. And code signing enables us to create a complex digest, which essentially allows us to testify that this is the program that I wrote and I signed, and there is no man in the middle who attacked the code and inserted bad actor code, which does things that you would not want the code to do. So then if you get a cabinet file that's been signed by Microsoft, it says, do you trust Microsoft? And if the answer is no, you don't run their program. And if the answer is yes, then you can, with reasonable assurance that the program hasn't been hacked in the transport layer as it came down to you. So then comes this next question, what's the role of the compiler when you have a Java virtual machine? And the answer is not clear. The Java compiler, javac, outputs bytecodes, but there's a just-in-time compiler in the Java virtual machine which takes those bytecodes and recompiles them down to the underlying iron or CPU of your computer. Well, this is very interesting because when you go to any kind of Intel desktop computer, after and including Pentium 2, it too has a compiler, and what it does is it takes the x86 codes, the legacy codes, and translates them into RISC codes internally. So this is so involved, right? Because you're taking Java source code, you turn it into RISC, that is reduced instruction set computer based bytecodes. The bytecodes are run on a virtual machine which uses x86 CISC codes, so that's complex instruction set computers. And then the Intel processor inside takes the CISC codes and translates them back into RISC codes. Right? This is like really messed up. So if you're running desktop processors like Core i9, it has a built-in overhead where it's trying to support legacy x86 codes that then get translated into RISC codes. Nice, right? So This may be one of the reasons why ARM processors have superiority in the mobile processing world. They don't have this extra overhead of having to support legacy x86 codes. So when we think about JAVAC, we only think about the Java compiler as it stands on the command line, where it takes Java source code and outputs byte codes. But there's still more compilation going on in the background that the Java programmer doesn't control. Neat, right? Didn't know this. So when we take the Java word and input it into the terminal prompt, we're invoking the Java virtual machine, which then takes the byte codes, runs them through a just-in-time compiler, and then that gets executed on top of perhaps an x86 legacy code processor, which then takes the complex instruction set codes and turns them back into RISC instructions. Nice. So messed up. So then here we have it, the compile time environment, and what it's doing is it's taking Java source code, converting it into a Java compiler. The byte codes, which are RISC codes, can move through the network, go into a bytecode verifier, which then can make sure that the bytecodes haven't been mangled during the class loading process. We go through and we examine the digest, which is accompanying the jar file that contains the bytecodes. And then once that's been verified, it goes through the just-in-time compiler or the Java interpreter. Java interpreter is interesting because it has extraordinarily low footprint, maybe 48 kilobytes. The just-in-time compiler is quite a bit larger, and then the just-in-time compiler will make the x86 codes onto the runtime system, which internally get converted back into RISC codes. So messed up. So when we think about the life cycle of Java code, source code goes into a compiler, goes into bytecodes, goes across the network, goes through the bytecode verifier, goes through a thing called a class loader, gets executed in the interpreter or just-in-time compiler, gives you your runtime classes, and interacts with the so-called security manager that makes sure that everything is running in the sandbox, or is having its feature limits lifted by virtue of a security manager. And the security manager is an immutable object. Once it's created, it cannot be altered. So if it gives you permission to delete all the files on your hard drive, that permission will be maintained during the life of the interpreter. So now we can discuss a little bit more about what a byte is, and I think everybody should know that that's a collection of 8 bits or binary digits. That a primitive data type is a mechanism that's used for holding small pieces of data, and there are perhaps, broadly speaking, 2 different primitive data types available. There are numeric data types and non-numeric data types. Right? And when we think about numeric data types, we can say there's basically 2 numeric data types, fixed point data types and floating point data types. Moreover, when we think about non-numeric data types, we say basically there's 2 different data types. The char, which is a 16-bit quantity, and what they call a Unicode character. And then there is the Boolean, which is either a value true or false. When we think about the floating point data types, there are also 2 different data types. One is single precision, and the other is double precision. Single precision being 32-bit, double precision being 64-bit. And then when we think about fixed point data types, there are 4, arranged in 8, 16, 32, and 64-bit lengths, 8 being byte, 16 being short. 32 is an int, and 64 is what we call long. And you cannot add your own primitive data types. Underlying this binary data, we have mechanisms for representation, and hexadecimal is one of the common mechanisms for representation. And you can see some hexadecimal examples here. Hexadecimal because there are 16 symbols, 0 through F, which are used for the representation of each one of the hexadecimal digits. Octal is also a commonly used radix or base for converting binary numbers into groupings that are convenient. This groups the numbers 3 bits at a time and has symbols 0 through 7, so there's 8 of those bits. And we call this base 8, and base is synonymous with the term radix. And so the radix of the numbering system is the base. It's the same. And you can use any base you like, but the common bases are base 10, base 2, base 8, base 16. In the case of UU encoding or Unix to Unix encoding of data, they use a base 64, but humans don't normally use such a base. Not normally, anyway. And when we want to write out the base, in base 10, for example, we can use so-called positional notation. So 42 is 4 times 10 to the 1 plus 2 times 10 to the 0. In binary, we write 1101. That's 1 times 2 to the 3, because it's in the 0, 1, 2, 3 place, plus 1 times 2 to the 2. Then we have 0 times 2 to the 1. And now we have 1 times 2 to the 0. 2 to the 0 is a 1. We add up all these numbers, and it comes out to be 13. So you can use a positional notation with the base and then the actual position in the exponent in order to be able to express any number in base 10. So primitive data types, they're built in, and as far as Java is concerned, you cannot change them, and so they are convenient mechanisms for storing bits of data and for doing computations. And so primitive data type includes Boolean. That's a lowercase b. The uppercase b is a reference data type. The 8 different primitive data types are divided roughly into character, well, let's say numeric and non-numeric. And here are another way to organize them: signed fixed point, signed floating point, char, and Boolean. And so when we think about primitive data types, we can say there are signed and unsigned. We can say there's numeric and non-numeric. It all depends on how you want to organize it. And here are a couple of examples. Chars are different from strings. They're surrounded by single quotes. And here's a classic way to express a statement. We follow it with a semicolon. And when we think about fixed point data types, we only have 4 available to us: byte, short, int, and long, with 8, 16, 32, and 64 bits each. So here are some examples, and you can see the byte range, because it's signed, it doesn't give you 0 to 256, it gives you minus 128 to plus 127. The most significant bit is the signed bit, and if it's set, then you have a negative number. The shorts also have an asymmetric magnitude. You can see the largest negative number, or perhaps smallest number, in short is actually not the same magnitude as the largest positive number in a short. That's because 0 is sitting in the middle as one of the numbers. So we can do the same thing with the ints, and then you can add numbers as you might expect with an imperative setting. So this says k is set to I plus j. So then subtraction can be done, addition can be done, division can be done. When you multiply, if you multiply a fixed point by a double precision number, you get a double precision number. if you're ever going to lose data during the process, then you will have an error. Otherwise, you might have to assert the explicit truncation of the data. So if you get something like 2.5 and you want to assert it to a short, what will happen is you'll have to cast that number to short data type because the 0.5 is being truncated away. If you use integer division, like we see here, 5 divided by 2, it just gives us the remainder 2, or the total number of times 2 goes into 5, which is 2, and the 0.5 is lost. Order of evaluation can be controlled with parentheses, as you could well imagine, but the operators also have a precedence, and division and times have equal precedence, and the precedence is greater than plus or minus. And you can print a random number by going to the library of math, the math class. That's a tool kit, and it has a bunch of static public methods in it, like random, and random will output a number that ranges from 0 to 1. So we've already seen an example of positional notation where exponents are used in order to describe the position of the digits. And we know something about already what an operator is. Operators like plus, minus, and division and times take 2 arguments. So the other operators, some of which are like negation, only take 1 operator and one argument. So operators, those are important because they make it easy to do computations, obviously. And binary operators take 2 arguments. Unary operators only take 1. Some of these unary operators are just abbreviations. So A plus equals is A equals A plus 25. A minus equals is A equals A minus 25. A divide equals is equal to A equals A divided by 4. So it's still looking like it's a unary operator because it's taking only a single argument, but in fact it maps to a binary operation. Then there's this thing which we call a truth table, and what this does is it allows you to use all the different possible inputs and show you what the outputs are. So this is a mapping that's done by what we will call perfect enumeration. And here is a bitwise operation equivalent to 2 switches operating in series. Call it the AND function. If X and Y are both closed, the light bulb will go on. That's supposed to be a light bulb. Here's an OR operation. X or Y go on, the light bulb goes on. Here's the so-called exclusive OR. So this one was called inclusive OR, although we just say OR. This is called exclusive OR because we exclude the case where both ones are equal, where both X and Y are equal to 1. They're both on. We exclude it. Bitwise operations in Java are important. They allow us to do hardware manipulation. A single AND percent gives us a bitwise AND. A single vertical bar gives us an inclusive OR. That is, through the bits in X and Y, we inclusive OR them together. The upper case, well, let's see, the up arrow gives us a bitwise exclusive OR function, and an unary function with tilde gives us a bitwise negation. These are different from and percent ampersand, 2 vertical bars, or the exclamation point, sometimes called bang, because these take as arguments Boolean data types, not binary data types, and it's important not to confuse these things. So the Boolean operations require that the arguments be of Boolean data type. And here are some examples of Boolean operations. So both A, and B, and C all have to be of Boolean data type. An augmented operator. Very interesting. Here's one called shift equal 3, and that says I equals I, shift to the right 3 bits. Here is I exclusive OR equals 9, and that's equivalent to I equals I exclusive OR 9. I really don't care for this clever bit of expression with uminary operators as they are augmented. However, they are available to you to use, and you may run into them, so it's good to see them. And that's what I have for you for today. Thanks very much for your time, and this should cover all of Chapter 1. Thank you.